Welcome to another episode of Transparent Physics. This one is associated with the unit moving in circles, and we're going to be solving some problems associated with the equations we discussed in the last video. The goal is to solve three different levels of problems. Level 1 should be pretty straightforward, just a base application of the equations. Level 2 should offer a little bit more challenge in terms of the math, and then level 3 is going to make a little addition to the difficulty, bringing in some physics from earlier in the year. So we're pretty well ready to set up. We got a nice open space for our problem. We got our TI 30X2S Texas Instruments calculator. Good solid calculator for solving problems. Got my pen. I would probably not recommend you actually solve problems in pen. You should probably use pencil, but for the sake of the video, we use a pen. And of course, got my cup of tea. Alright, and special guest star today. Whenever we're solving problems, we're going to try to focus on our QUIPS problem solving strategy. And to help us out, again, we got our QUIPS, I don't even know what to call it, snack column, quick something or other. And as I do each of the three, or each of the 5 topics in QUIPS, I'll treat myself to a little snack as well. Today's snack treats are tiny conversation hearts. So lots of different flavors there, artificially flavored. And I don't know, I remember them from being a kid, so maybe it'll bring back some memories. But let's get right on it for question level 1. So we've got an old-fashioned record player. Ask your parents about them if you don't know what I'm talking about. And it's got a record player, vinyl, I guess what we call it nowadays, playing a copy of Kenny Rogers. Salute to Kenny Rogers there. And it's from his album The Gambler. Now, if I remember correctly, The Gambler is one of his best-selling albums. I think 35 million copies. So go ahead, take a listen to that after you're done with this video. And it's spinning at 33 1/3 RPM. I did the math for us on this one, although it's not too crazy. If it's 33 1/3 revolutions per minute, that ends up being about 1.8 seconds per revolution, and that is capital T, which is period. So we've got a record spinning on a record player such that it completes one revolution every 1.8 seconds. We got a roly-poly bug. Roly-poly bugs are the little guys that are, I don't know, they sort of look like this, and you got little segments here, and they got a bunch of little legs, and then if you bug them, then they sort of go up in a little ball. I think sometimes they're known as pill bugs as well. Honestly, I think growing up I called them potato bugs, but apparently that's not the right term for them. So that's a roly-poly bug. So we got a roly-poly is standing on the edge of the record, and we're going to say that from the center of the record, the roly-poly bug is 29.5 centimeters away. And fun fact too, roly-poly bugs aren't actually bugs, they're actually a type of crustacean. So fun facts. All right, so assuming that we got the roly-poly bug set up like this, we want to know what the speed of the roly-poly bug is in meters per second, so they specify that, and what is the centripetal acceleration of the bug. So we've gone through, we've read the question, which brings us to, let's take a look at our first one here. Is that focusing? You and me. You and me. Vague enough, I guess. Very crunchy. All right. So what do we got here? So next up, might as well not make that go too far. Let's underline our important information. 33 1/3 RPM is good, but it's really only important in the context of knowing the period. Roly-poly bug spins a distance of, so that's probably going to be important there. We're interested in the speed, and they specify it's meters per second, and we're interested in the centripetal acceleration. So it doesn't really seem like we're given a ton of information to start, but we'll take a look, and hopefully our formulas will be enough to get us where we need to be. So I underlined. Totes. Totes. Oh. That is totes good. All right. Next up is the I. Looking for information. Probably going to include a sketch. So if we do an overhead view, again, it does not need to be an illustration. It just needs to be something just to get the basic idea down. So I'm going to draw a circle. That's my record player. I mean, maybe if I want to, I can make it look a little bit more like a record player, but that's about it. And we got a little roly-poly bug. The roly-poly bug is at a distance from the center. And I'm going to list that as R is 29.5 centimeters. We also know the period, which is 1.8 seconds. And we are interested in the speed in meters per second. Notice I wrote the units since they specified that's what we want. And we want to know the centripetal acceleration. So we got all the information we read here. Little problem here, centimeters and meters are not the same scale, so we're going to have to do something about that. Usually we take centimeters, convert it into meters. We're going to use the factor label technique. There's probably going to be a video uploaded about that if it hasn't already been done so already. We want centimeters to cancel out. We put it on the bottom, meters on the top. In 1 meter, there are 100 centimeters. So we're going to take 29.5, divide by 100. If you're good at this, you probably don't need to show the work, but it's 0.295 meters. So you can't have centimeters and meters in the same formula. You've got to keep them separate. All right. And then during the information phase, we've got the knowns, we've got the unknowns, and we've got our sketch. So we put all that together, and that's everything that we've been given. So we are done with another phase here. And laugh. Indeed. Oh, all right. All right. So next up is our procedure. We got a link. What we know to what we don't through equations. Now first we are interested in V. We want an equation that has V, T, and R in it all at the same time. So in my estimation, I mean, if we take a look at our equations, we have V equals 2 pi R over T. We have AC equals V squared over R. And we have a variant of that, AC equals 4 pi squared R over T squared. So those are our equations to pick from. We want an equation that links what we know, which is R and T. We want to link R and T to V. So that's a pretty clear pick that we're going to go with this first equation. And we are interested in solving for V. Bonus, it's already ready to go. So we're just going to write V equals 2 pi R over T. And we know all the information. The units have already been squared away for us. So we can just plug and chug. So 2 pi R is 0.295. T is 1.8 seconds. Check the units. You're going to get meters per second, which is good. That's what we want to see. So units work out okay. And that's what we're going to do to get our answer. Looking ahead very briefly. Well, really, let's pause for a second. In the QUIP's problem-solving strategy, the idea is that we get the information, we establish a procedure, and we get a solution. Now, this might repeat a couple times. Like for part A, I'm pretty much done with the procedure now. I can just skip to the solution. So we're going to wrap up QUIPs, but we're going to come back to it again for part B. So let's take a look here for procedure. It is cool. I agree. Physics is cool. I agree. All right. Let's get the solution out of the way. Bring out the Texas Instrument calculator. This video is not sponsored or endorsed by Texas Instruments. I just think it's a pretty solid calculator. All right. So 2 pi times 0.295 divided by 1.8 gets us that. So 1. Let's just say 1.03. Technically with this, if it's 2 sig digs on the top, 3 sig digs on the top, 2 sig digs on the bottom, I should round to 1.0, not 1.03, but for the sake of this video, we'll leave it as 1.03. I'll just make that a little more precise next time. And that's it. I do also encourage you to circle it. Does it make sense? It's going about a meter every second. Well, their circumference is 2 pi times 0.295. So, well, the circumference, the whole circumference is about 1.85 meters, which honestly is bigger than I thought it would be. So, since the circumference is almost 2 meters and the period is 1.8 seconds, the idea is that you're covering roughly about half of a period in this time period. I mean, you're covering in 1.8 seconds. We've got our distance divided by our time. So yeah, I mean that's a decent distance to travel in 1.8 seconds. So divide that basically per second, which is about half of it. That makes sense. It's about 1.03 meters. Given that you're almost at 2 when you're around 2 seconds. So for round 1, you'd be around 1. So it makes sense. A little faster than I thought it would be, but sometimes physics works out that way. So, you know what? We're going to save this last S until we're done with the whole problem. Just a little treat at the end there. So, all right, so part B asks us for the centripetal acceleration. Let's get back focused here. All right, so what do we do? Well, we actually have a couple of choices here, maybe. We did just solve for the speed. So if we're looking for the acceleration, we have 2 equations for acceleration. We just found the speed, and we were given the radius to start. We also know the radius, and we were given the period to start. So at this point, I have a choice. I can use either of those 2 equations to solve for acceleration. I'm not sure. It looks like there's really an advantage one way or the other. So we'll just stick with the shorter equation at that point. So we're just going to choose AC is v squared over r. And we're going to take our speed that we solved for in part A, 1.03 meters per second. We're going to square that. And then we're going to divide that by 0.295 meters. At this point, it's always nice to take a quick check for the units, so I'll do that over here. This is meters per second squared divided by meters. Meters per second squared is meters squared second squared. Dividing by meters is the same as multiplying by the reciprocal. Meter cancels out, leaves us with meters per second squared. So that's good. Those are the units we want to see. So let's go back here, work out our math. Do not forget to square. Super common mistake in introductory physics is to have everything written down and then forget to actually square it. It's not going to make a huge difference here with the number, but for other problems it could. So 1.03 squared divided by 0.295. And the centripetal acceleration the Rollie Pollie bug is going to experience is going to be around 3.60 meters per second squared. All right, let's take a look back here. All right, so we established that the speed using v equals 2 pi over t is equal to 1.03 meters per second. And from there, we plugged the value we got for part A into part B, although we could have done it a different way too if we wanted to. And we got an acceleration of 3.6 meters per second squared. A little hard to get a sense for whether or not that answer makes sense in terms of the acceleration. we don't have a really good instinct for interpreting accelerations. But if we were to put it in the big picture, an acceleration of 9.8 meters per second squared would be the acceleration that you experience, equivalent to sort of your weight from gravity. So this would be, roughly speaking, a little more than 1/3 g, putting it in that context. All right, I think we've gotten that all done, so you know what time it is. Let's see where we wrap up. Ah, BFF, awesome. Okay, well, that is a level 1 problem. Next up, we're going to see something that's a little more difficult with level 2. Thanks for tuning in, making things a little bit clearer with transparent physics.